So first of all, before starting, I wanted to really thank the organizers, in particular, of course, Mathilde and Patrizia, for inviting me here. I can say it's the first time for me here in Cargèse, and it is just wonderful. It's really very delightful to talk. I mean, this is a very inspiring meeting, but also, of course, environment, and this together is just why we are doing physics, I believe. Okay. Good. So where do I have to press here? Okay. So this is another talk on collective photon emission collective photon emission, as we just heard it before, and as we heard some talks yesterday. And in this case, I will talk about correlated atoms, as we had discussed it a little bit also, or you had discussed it a little bit in the former talk, but coming from a different perspective. Instead of excitation, single photon excitation, where you create the correlations, I will start usually from the fully excited state and via detection create the collective states. And this brings together these two fields, which are in principle very separated. The Dicke superradiance, of which you were talking already, by a single photon excitation, and the DLCZ protocol, for example, exploits this phenomenon of collective emission via creating a collective state and then producing kind of superradiance. You were mentioning it already. But since I come from the fully excited state and all this is created via detection, this brings us in the realm of Henry-Brown intensity interference, and which we also heard a lot of times, and brings it together to the talk by Arno of yesterday. Where is Arno? Here. Exactly, where you were saying that the G2 function is a conditional measurement. You were pointing out for two detections. The first detection conditions our state, and the second detection measures this correlation. And I will extend it not only to 2 photon correlations, but n photon correlations and many conditional measurements. So this brings together these two very different fields, as I just said, of Dicke superradiance and Henry-Brown twist effect. And we will see there, in effect, two sides of the same coin. And this is all the more surprising because both papers are more than or almost 70 years ago written, and they're very discussed up to today. I mean, heavily investigated up to today is, of course, Henry-Brown twists, in other words, G2 or GM measurements. And superradiance is still under hot debate. It's a very enigmatic paper, and people read it, and the calculations are all correct. Nobody doubts the calculations. But the interpretation is still discussed heavily, even today. So all the more, the people didn't know each other, I assume, but they're closely connected. And on the other hand, these two papers are more or less also the birth of quantum optics. This is at least what Glauber says in his Nobel Prize lecture, that this surprising result of 2 photon interference intrigued him, and he wanted to understand better what is going on. And then he developed his theory of coherences of higher order, which we will investigate today as well. But we will also see how this is closely connected to this other phenomenon of superradiance. Okay. Having set the stage, I just say that I will very slowly start. I mean, Young interference, first order coherence, everybody knows. I recapitulate so everybody can enter it. And then we go one step further, we go to second order coherence and discuss Henry-Brown twist. And in between, I will discuss a phenomenon of Dicke superradiance, and we will ask ourselves, how does this fit in? And we will ask a question, and then we go in more detail into the discussion of superradiance, and where it is coming from, I mean this collective state, as we will see, and then we will make the link to the conditional measurements and then to a Henry-Brown twist approach. And then I present some measurements of where we obtained our theory and this combination of Henry-Brown twist and Dicke superradiance in real atomic systems and also in classical systems. Okay, now, as I said, let's start with a very simple approach. First order coherence, as investigated and proposed and measured by Young almost 200 years ago, or more than 200 years ago. You know, if a spatially coherent wave impinges on a double slit, you will get an interference pattern on the screen. And of course, we nowadays in the modern language, we discuss this on a single photon level, where again, you need a wave function of a single photon which is spatially coherent. Only then the phase between the two paths the photon can take is stationary and not changing all the time because of incoherence. And so you get a stationary interference pattern if you measure more and more photons accumulate to come to the macroscopic regime, which was discussed by Young. But nowadays, in the modern language, of course, we know that this is a accumulation of single photons where each photon interferes with itself, and the interference between different photons never occurs, as stated in this famous statement by Dirac. Okay, so we can then go one step further and go on to the microscopic level, where we have the same phenomenon realized not by individual slits, but by individual atoms, where again, as we learned yesterday by Arno, if we very smoothly excite the atoms, smoothly means very much lower than the saturation intensity, then most of the light is scattered coherently, and then again we can replace the two slits by these two atoms because they scatter the incoming wave coherently, and so we would obtain exactly the same interference pattern. And this has been measured more than 20 years ago in the group of Dave Wineland in this very nice experiment, which was cited yesterday by Lucas. Where's Lucas, by the way? Here, Lucas, okay. Very nicely, this famous experiment a very nice experiment in the Dave Wineland group, where you can see here two atoms stored in a linear Paul trap, and here you see the far-field interference pattern and the fringes depending on the distance of the ions, as we would expect from a first-order coherence. Okay, now, as Lucas pointed also out yesterday, more than 20 years we did the same experiment. We just repeated, I would say. Now using calcium atoms instead of mercury atoms, also again in a linear trap. Here are two ions trapped, and we see these fringes as is shown here. But we went one step further, because we wanted to explain what Wineland already pointed out in his experiment, that if you don't drive the atoms smoothly, they will stop to scatter coherently, and they start to scatter incoherently. That is via spontaneous decay. And this is, just to mention, instead of only two ions, we also measured 3, 4 ions and 4 regular ions, so that is fine. But what I wanted to point out now here is that we investigated this incoherent scattering. As you can see here, the scattered intensity, the incoherent part, as pointed out by Lucas yesterday and also by Arno, increases if you drive the atom stronger and stronger, whereas the incoherent part goes slower. So the incoherent part will not produce such an interference pattern, and this is exactly what we investigated. I just pointed out here in theory, this is a first-order correlation function that is an interference pattern on the screen. For low saturation, you see here a modulation which, if you calculate it, has a visibility of 100%. But the visibility decreases with more higher saturation of the ions, because the incoherent part dominates. And in this case, and this is what I wanted to show here, the visibility goes down. So we go into this regime where the light is becoming more and more incoherently scattered. So that was new in this paper. And it is, in fact, exactly this regime I'm interested in, and I could go to the extreme where both atoms, by some means, are initially in the excited state, okay? So instead of coherently, smoothly driving the atoms with very dim light so that they scatter coherently, I'm in the fully excited state, so certainly both a photon, if scattered, will be scattered incoherently via spontaneous decay. And here again, the two quantum passes which are possible, but now with a fluctuating phase from shot to shot. And if I make one shot, of course, I have one phase phi1 and one phase phi2 for a particular pass, and the probability of detecting a single photon would look like this. But in the next pulse excitation, the relative phases would shift, and from pulse to pulse, they would shift, so that altogether, I do not see, not at all, any interference pattern, obviously, because the photon is scattered incoherently. So this is not a surprise. I can do the calculation, and I will come to this later. I mean, the calculation is done by looking at the electric field as a superposition of one atom going from the excited state to the ground state and accumulating a particular phase from the atom towards the detector, and the second atom going from the excited state to the ground state and accumulating a different phase from the second atom to the detector. So this is my experimental modeling. Theoretical modeling. And if I do the calculation for the double excited state, I obtain indeed that the G1 function is a constant. So this is from a calculational point of view, everything is fine. But we have a third interpretation, which is also very helpful. That is from the perspective of which way information. And the idea is if you are in the fully excited state and one photon is scattered, then you have full Witch path information that either the first or the second atom has scattered the photon. So the two final states which are possible in that case are completely orthogonal, meaning that you have full which-way information, and as we know, if you have full which-way information, no interference pattern can be obtained, and so also from this perspective, everything is okay. Now I turn to a different initial state, namely kind of dipole emission, where the atom is in a coherent superposition of G and E, that is leading to non-diagonal elements in the density matrix, so representing the coherence, so to say, a dipole emission. And I apply again this which path information. As you see, I mean here, having both atoms in the coherent superposition of G and E, either the first or the second one, and I emit a photon, then I will go from BE1, for example, to BG1, or if the second atom emits a photon, I will go from beta E2 to beta G2. And you can see if this is my initial state and I emit a photon either via the first or the second atom, I will go into a final state which has an overlap. So I do not have full Witch path information. I do expect interference fringes to appear. And if I do the calculation, indeed, I obtain it depending on beta and alpha. And so I get an interference pattern. So we understand if there's a dipole emission, I mean a classical dipole, so to say, modeled here by a quantum mechanical expression, we obtain an interference pattern, but I am in the fully excited state. Just via which-way information, I fully understand that I don't get any interference pattern. Okay, now I'm coming to a Dicke state, which is an entangled state, and a superradiant state, as proposed by Dicke. Look at this. There's no dipole dipole moment in the state. It is not a coherent superposition of E and G for the individual atoms. It is EG plus GE, okay? But it is also not the double excited state. So what do I obtain here? And if I do if I look from which path information, I can go from this state to the ground state or from this state to the ground state, and the final state is a complete overlap. So you would expect from this state a fully interference pattern and with a 100% visibility, and this is indeed what you obtain if you do the calculation. So from this particular state, and we will discuss it later on in more detail, you also obtain an interference pattern, even though there is no dipole moment in the system. Okay, this is very surprising a little bit. It is spontaneous decay, by the way, very important, which is exactly the reason why Dicke coined his paper coherence in spontaneous decay. So we have spontaneous decay here, but due to the fact that we are in a Dicke state, we obtain an interference pattern. This is a little bit funny, but this is exactly the enigmatic thing of the paper of Dicke. And to confuse you even a little bit more, I go one step further, and I go to two photon detection. I have two photons in my system if I'm in the fully excited state. And the idea comes, of course, from astronomy, where you also, not we, but Henry Brown Twiss at the time, also almost 70 years ago, wanted to obtain the distance between two incoherently emitting stars by having a two-photon detection. Okay, so miniaturizing the whole thing down to our optical tables, where we replace the two stars by two atoms spontaneously, incoherently emitting a photon. Then we set up this two-photon detection. This is our G2 function. And again, without going in all the details of the calculation, we understand from a two-photon path interference, where either a two-photon path is according of this configuration, where atom 1 emits a photon which is detected by detector 1, and atom 2 emits a photon which is recorded by detector 2. This is one two-photon pass, and another one where 1 goes to 2 and 2 goes to 1. And they have different phases, they interfere, and I go from the initial state to a final state where I'm completely in the ground state, full overlap. And again, I get, from this perspective, two passes, same initial state, same final state. I would expect an interference pattern, and indeed I get an interference pattern. Again, completely spontaneous emission of the photons by having a two-photon detection. So the question is now, is there somehow a link? I mean, because between what I discussed in this configuration here, having a Henry Brown Twiss setup, and in particular the former situation where I discussed the situation where I was in a decay state, where in both cases I obtain an interference pattern which has a visibility of 100%. And the answer is yes, there's a strong correlation, and I will discuss it, and not in the next chapter, but in the chapter coming thereafter. First of all, I would like to have a little recap of what is superradiance, and maybe coming to the paper which was written by Dicke in 1954. And maybe I remind you very quickly that spontaneous decay of a single atom, Arno has discussed it yesterday heavily, is of course you go from the excited state into the ground state via an exponential decay of a probability that a photon as a function of time is detected. And, but going then in a situation where you do not have a single atom, but many, many atoms, initially fully in the excited state, the whole thing behaves very differently. And that is exactly the content of the paper of 54 by Dicke. Namely, if you are starting from the fully excited state and one photon is recorded, as we just learned by Daniel, then you are in a Dicke state, but from above. That is, one photon is detected from the fully excited state. That is, all atoms are in the excited state except one, but you do not know which one. So you have to write this in a coherent superposition of either the first, the second, the third, or the nth atom in the ground state. Exactly as you pointed out before, but from the excitation point of view. Here it is from the detection point of view. If a second photon is detected, then again we are in a double, in the double ground state system, but we do not know which atom is in the ground state. So we have to write it as a coherent superposition. And now if we look at the function of time, starting from the fully excited system, how the intensity would be as a function of time behave, we see a completely different behavior as a function of time, namely not an exponential decay, but a peaked intensity which is going down. And the peak here in the middle is proportional to n squared, as if the light would be emitted coherently. And that is the title of the paper, Coherence in Spontaneous Decay. All this is spontaneously emitted photons. And the question by Dicke was, how is this possible that we have an n-square law, as in a coherently illuminated grating, whereas the emission is completely incoherent? And that is the title of the paper, Coherence in Spontaneous Emission, and we will discuss where this comes from. And in addition to having this behavior, in addition to having this behavior as a function of time, we also can see that in a certain direction, if one direction is, for some reasons I will discuss later, somehow very special, we will have in this particular direction intensity proportional to n squared. Okay, so again I repeat what I said before. All these states which are listed before here, all these Dicke states, don't have any dipole moment. The dipole moment of each individual Dicke state is 0. And that is somehow in opposition to many explanations of this phenomenon, where the people say, well, if initially all atoms have been initially in the excited state and a photon is emitted, the other atoms somehow feel the field of the spontaneous emission, they go in phase, they synchronize, and then they oscillate in phase. I'm very happy, Jacopo, that you also, I'm shaking my head all the time since many years, but many people do this, you see. I mean, this is, I would say, the standard explanation so far. If, you would read in 90% of the papers explaining superradiance, but it is obviously not correct. I mean, this is not a phenomenon of dipole moments, as I discussed before, and not a phenomenon of synchronization, because the dipole moment in any of these states is 0. Okay, now we could ask, where does this come from, and this behavior? And for this, I model the whole thing for simplicity in a linear chain of equidistant atoms. It mustn't be like this, but it simplifies the calculation. And again, my total field is a superposition of the lowering operators and the accumulated phase from each atom towards the detector. And now I want to calculate the intensity as usual, as the modulus squared of the field, I mean a quantum mechanical way, of course. And as we will see in a moment, this depends heavily on the initial state. And to make it very simple, let's start with 2 atoms in the excited state, and the photon is detected. Then, of course, what could happen? either the first atom, as we discussed before, emits a photon, or the second atom emits a photon. We know that the final states are orthogonal. A certain phase is accumulated in both cases, but the final states are orthogonal. So if I calculate the intensity, I take the modulo square of the sum, but since they are orthogonal, I simply get this modulo squared plus this modulo squared, an incoherent sum, so to say. And I get a factor of 2, and I can normalize, so this is my intensity, which I would have if I have this completely separable state. But what would happen if I look for a Dicke state here, where again we have 2 excitations in the system, but 1 atom in the ground state, but you do not know which one. So you would say, well, there's not much going on. I mean, the 1 atom in the ground state, I mean, no more energy in my system. The only thing is that I do not know which atom is in the ground state, but so what? But a lot of things are happening. Due to the fact that you do not know which atom is in the ground state, you are in a collective state, as discussed in the talk before, and you have this coherence, which is reflecting the entanglement of the state. And I will show you now in a second how this works. I mean, let's go term by term. Let's look for the first state, which is the state of before. Of course, the first 2 atoms are in the excited state, and I can go down either from the first atom emitting the photon or the second atom emitting a photon, orthogonal states accumulating corresponding phases. The same is true for this term here, but here it's the first and the third atom going towards the ground state accumulating particular phases, but they are orthogonal again. And for the last term, it is the second and the third atom which could go to the ground state, as shown here, accumulating particular phases, but they are orthogonal. So far, so good. But since we have a plus sign here, and since we can recognize that this state and this state are the same, and this state and this state are the same, and this state and this state are the same, and we have coherence due to the entanglement, if we take the modulo square, then, of course, we get interference. And the interference results from the entanglement of the system. And if we do the calculations, then, of course, we have to take the final states which are identical and take the modulo square. So it is not anymore an incoherent sum. It is a sum of coherent parts, as you can show here, and we get a different intensity, which is twice as the one before. And we can generalize this, and I sum it up. I explained the example of 2 excited states, but if we do the entire calculation for any number of atoms, where the total number of atoms is given by n, and we have a certain number of atoms in the excited state, a certain number of atoms in the ground state, but again, we do not know which atoms are in the ground state and which are in the excited state, then we look for the number of final states which are possible. In my example on the transparency before, there were 3 different final states. I look for the total number of passes which go to this particular final states. I take the normalization into account, and I arrive at a very simpler formula, which is exactly the same formula as derived by Dicke in 1954. So from this quantum pass explanation, we understand where this comes from, and I stress and repeat again, this is due to the entanglement of the Dicke states. Okay, in particular, one can solve the, one can point out again what Dicke pointed out. If half of the atoms are in the ground state and half of the atoms are in the excited state, I have an intensity proportional to n squared, even though the emission is completely incoherent and spontaneous. I mean, this is what he pointed out, of course, already in his paper at this time. Okay, and this is exactly what we obtain here. Now, if I take into account, so far I calculated the maximum intensity of the whole thing. Now, if I take the phases into account, if you remember 2 transparencies before, I discussed also the phases, what I will see is that I obtain in this configuration of a linear chain, which has a forward direction, that I get a very peaked emission in the forward direction, and again, in the forward direction, yeah? In the forward, of course, in the forward direction, and again, because only due to the, no, not only, even though the emission is spontaneous. This is what I wanted to say. I mean, we have a behavior as if we would illuminate coherently a grating, but the decay is completely spontaneous, and the coherence comes from the entanglement of the system. Now, I discussed symmetric states here. As you can see here, I took here the particular example of 1 excited state, and the rest of the atoms are in the ground state. And as if you do the calculation, you can see that this then is proportional. The maximal intensity is equal to n, even though I have only 1 excitation in my system, yeah. But the peaked intensity in the forward direction is equal to n, and the width of this resonancy is going down with 1 over n. And of course, I can not only consider symmetric states, but I could also consider non-symmetric decay states, which also exist, and then I would obtain an anti-resonance in the forward direction, a so-called subradiant emission in the forward direction. Okay, so once we have understood this, now we can ask the question how we can produce these decay states. It's not so easy, by the way. It's very difficult to produce decay states, and not so many experiments have been done in the past. And so here's our proposal. We use conditional measurements, as was pointed out by Arno yesterday. And conditional measurements means I take, for example, G2, where my first detection, as I will show in a second, produces the entangled state, and my second detection then measures this entangled state. And so this can be generalized. I will come back to this in more detail. This can be generalized, not only measurements of G2, but of course measurements of Gm, where I have m detections in the far field for n atoms along a line, for example, and then I would look for the mth order correlation function. But I will go to this now in very much detail. And I come back to the second order correlation functions for 2 atoms in the excited state. And now we can interpret it from a different point of view, not from 2 photon quantum passes which interfere, which is a very useful interpretation, but here I would like to take a different interpretation. Here I take the interpretation that my first detector records a photon and projects the double excited state in the far field into a decay state. Because in the far field, this detector cannot know where the photon is coming from, so it could be either the first atom which has emitted the photon or the second atom which has emitted the photon, and I have to take into account the relative phase of these 2 different quantum passes, as is shown over here, and this is my final state upon detection, and that is a decay state. And now, in the next step, I detect the spatial behavior of this decay state. But this we discussed heavily in the section before. I know it already what is happening here. This is a G1 function, the intensity of a decay state, of this decay state, and I can calculate it, and I obtain here this particular form as a sinusoidal variation with fulfilling this formula where Ng1 atom in the ground state is 1, Ne1 atom in the excited state is 1, and so the maximum of this curve is 2, so fulfilling this maximum emission probability in the forward direction, exactly according to the decay formula. So this is decay superradiance, what I observe here. Yeah? So I produce a decay state and then detect the intensity of the decay state. But at the same time, it is of course also a second order correlation, cross-correlation measurement, where I calculate as usual, in the usual way, as Arno did yesterday, Lucas did yesterday, and everybody does. You can do the calculation, and you obtain exactly the same result, of course. But this is what we call a HPT measurement. And so this is a point where I want to stress heavily that superradiance is an HPT measurement, or better to say HPT probes superradiance due to the conditional measurement. Okay, so this is, it's one thing, it's one and the same thing. And I repeat again, these 2 papers were written 70 years ago. They didn't know each other. One is writing this, the other is writing this, but this is heavily the same phenomenon. Okay, of course you can generalize this, as I said before. I mean, we could have n emitters, m detectors, start in the fully excited state. I could measure 1 photon, then I have n-1 atoms in the excited state, 1 atom in the ground state. I do not know which one. I have to take into account the particular phases. I make a second detection, 2 atoms in the ground state. I do not know which one. I have to take into account the corresponding phases, and so on and so on. And the final detector then, which is moving around here, detects a decay state where m-1 atoms are in the ground state, and m-1 atoms are in the ground state, and the remaining atoms are in the excited state. It's a complicated decay state. I measure the intensity of the state and will obtain a certain result. But of course, at the same time, it's a mth order correlation measurement, and I can do the calculation, and just structurally I can say it is exactly the same as we discussed on one transparency, where I have to take into account the different final quantum states and the different passes which end up in this particular quantum state. And so this gives rise to an interference. This is an incoherent sum of the final states. So structural wise, it's exactly the same formula as we were discussing by hand in the example of 3 atoms where 2 of them were excited. Yeah, sure. Sure. Go back for the 2? Sorry, I go in the wrong line. Yeah. Correct.
That sounds odd to me.
Yeah.
Because the far field is defined is lambda over 2 pi is the near field, and when I go much larger than lambda over 2 pi,
Mhm.
I'm in the far field. If your ions are 1 meter apart and the photon comes at 90 degrees,
No.
either from one or the other, the detector knows from where the photon comes. So that doesn't have to do with the. In the end, it must be the resolution, so that like if I propagate the light backwards, I have a point spread function that is larger than the distance between.
You could link it to that, absolutely, but I will point out a little. I mean, I come from the other point of view, and I will tell you, think of this detector not as here on the screen, but very far away, so that the two k vectors are parallel.
Yeah, okay.
This is what you're usually doing also in a grating. Huh? I mean, if you calculate it.
But it's not the far field, it's some other condition.
You name it as you like.
With respect to one ion, and then if I'm much farther away than lambda over 2 pi, I'm in the far field.
Well, some opticians here, I mean, I don't. I mean, let's, whatever we talk, I mean parallel k vectors. I mean, let's define whatever. For me, it's a far field, but maybe it's not the right coining. Yeah, absolutely. I'm talking about the Fraunhofer regime. Absolutely, yes, yes. That is certainly a good coining. I will use it in the future.
Being at infinity or whatever, you could put a single mode fiber entrance here.
Here?
The point is just to couple to a single photon mode.
Absolutely. Absolutely. I could use a fiber here, mix it, and then lose information for the atom. Absolutely true. I mean, I'm just, since I use it later on for, well, I will not talk about this, but since we are using it for imaging, you see, so I like to stay in the free space, and I mean, without any supplement, but you're completely right. The essential point is to lose information where the photon is coming from, and this is, of course, perfectly possible also with fibers, yeah. And I will use the word Fraunhofer limit. That's okay. Okay, so where I was explaining this, yeah, and now I want to come to in a particular configuration where the m-1 detectors, which are at a fixed position, and the last one, as before, is moving, and the first m-1 detectors are at the same position. And because I do this, because the calculation is particularly simple, again, I start in the fully excited state. And if I do the calculation of the m's order correlation function, I come here into a formula which many of you might remember. This is just a grating formula in a different term. And so the grating formula here with a certain visibility, which is given by this a little complicated expression. But again, as before, if you remember that the width of the peaks is going down with 1 over n. And maybe it's better to show some plots. Here it is with n equal 2, n equal 5, n equal 3, n equal 10, where the number of detectors in this particular case is the same as the number of emitters. In which case, if you look for the calculation here, the visibility is 100%, as you can see here, and the width is going down and down and down. Again, I repeat again and again, even though it is spontaneous emission. This is a surprising phenomenon of Dicke superradiance. And we did this measurement, and I'm not so bad in time. I'm happy. Okay, so we did this measurement, and so far I explained everything from a pulsed excitation. I mean, even in this calculation here, I was saying that initially we start from the fully excited state. Now, you can do this, but then you have to repeat and repeat many, many times. So it is more easy to do it in a CW laser-driven configuration. And if you do the calculation, you solve the master equation and anything, then of course the saturation pops in. As I said before, it is of course very important, the saturation parameter, but the structure of the whole thing does not change very much, as we have here, again, for 2 atoms and 2 detectors, a visibility of 100%. And cosine modulation, as we were finding out and calculating if the 2 atoms were initially in the double excited state. The normalization is also a little bit different, but otherwise, structure-wise, the whole expression is identical. And so, as I said, the first detector then will project onto a particular Dicke state, depending on the relative phase of the 2 passes, either from atom 1 towards the detector, or atom 2 towards the detector. And so let's think that I put my detector in the middle of the 2. So I have a symmetric configuration where this delta 1 is a multiple of 2 pi. So there's a plus sign showing coming up. Here I have to take into account these deltas, this position of the first detector, which is showing up here. So I plug it in. And I calculate the whole thing, and it is indeed, as discussed before, we have super radiant emission in the forward direction, a maximum in the forward direction. And I can, as I said, solve also the master equation of the whole thing, and so I don't know only the situation at tau equals 0, but also tau varying in time. And here an interesting phenomenon pops up, which was discussed also yesterday in the talks by Lukas in particular, but also Arno was pointing out it shortly, that surprisingly, even though we have super radiance in the forward direction, repeatedly, periodically, yeah, so the forward direction, as you can see here, it goes up, the G2 function goes up, so I observe anti-bunching in the direction of super radiance. And that is a little bit surprising. I mean, super radiance and anti-bunching you would not put immediately together, but I go back to the 2D projection here, so you can see it as G2 is below 1 here, so this is a maximum in the forward direction, that is true, but after in time it goes up, as you can see here. Here in time it goes up, so we have anti-bunching. And the reason for this is the following. So if we have a symmetric detection, I mean my first detector is in the symmetric configuration, and if I look for the autocorrelation function, this is what I'm doing here, the autocorrelation function, if I talk about anti-bunching, I look only for one mode, not the cross-correlation. I have to put this detector also at this position, so I'm sensitive for the symmetric decay channel, as we call it, from EE double excited state to symmetric state to the ground state. And if my saturation is not very strong, the population in the symmetric state is much, much larger than in the double excited state. And the ground state, of course, is the largest population. So I'm more or less back in a two-level system here if I look for the super radiant decay channel, so to say. And that is the reason why I obtain anti-bunching. Okay, so super radiance goes together with anti-bunching. Now, let's have a look if I go to an antisymmetric position of the first detector, as shown here. I mean, here I assume that the path difference between the two passes is an uneven multiple of pi. Then I get a minus sign over here, which I have to take into account in this expression. And then what I obtain, indeed, in the forward direction is subradiant emission in the forward direction here. And if I look for the whole thing as a function of time, the G2 function, then I see indeed subradiance in the forward direction. But for the autocorrelation function, where I put my second detector again on top of the first detector to detect the same mode in this antisymmetric decay channel, so to say, this is this decay channel, which I cannot populate by the laser, this antisymmetric state, because it's a laser, we discussed it yesterday in one of the talks it was pointed out, the laser couples only the ground state to the symmetric state and not to the antisymmetric state. So the only possibility to populate this decay path is via the double excited state where one photon is coming after the other. So that is the reason why you here obtain bunching. So what you see here is subradiance in the forward direction, but if you look at the same mode here, we obtain bunching goes together with subradiance. A little bit surprising, yeah? I mean, so this is not what one probably would expect. Okay, so we measured this also. Again, our calcium atoms now with a camera. And what I should say, I mean, as you could see here, the proposal, the proposal is a long time ago. I mean, where is it? Oh, maybe not here. Here, exactly. So the proposal is many years ago. And we could not, now I have to speed up. No, we could not do the experiment because you need a very, very fast camera. I mean, a large camera with 1 million pixels and nevertheless picosecond time resolution. That is not so easy to obtain. And we found it in the life science community somewhere, and we collaborated with a company, and very, very nicely we could make use of this camera. But we needed two cameras as a usual Henry Brown twist-up setup, because the dead time of this camera is 100 nanoseconds. So one photon detected, the second photon detected must come on the second camera. So we did this experiment, and this is the result for the different. I'm a little bit surprised. That is a little bit quick, but maybe it is okay. So for here is indicated the position of the first detector, meaning in detail the pixel of the camera, one particular pixel here of this camera, one particular pixel, conditioning on what entangled decay state I project my two calcium atoms. And then with the second camera, I detect here as a function of time delay and also as a function of position where the next photon is coming. And then I get an histogram. And you can see already from looking by eye that the histograms look differently because I project on different entangled states depending on which pixel I select for the first photon detection. And I remind you again, superradiance in the forward direction with anti-bunching is looking like this in theory. Subradiance in the forward direction looks like this with bunching according to what I showed here. And so this is our result. So in the forward direction, we obtain indeed a superradiant emission in the forward direction if we have a symmetric state. And we have a subradiant emission in the forward direction if I project onto the antisymmetric state. So this is the experimental outcome. And of course, I could choose anything in between. Pixels not necessarily going on to symmetric or antisymmetric, but any different phase which I can select depending on the pixel which I select over here. And so I get all different kinds of entanglement and all different kinds of G2 functions. And just to point out also, this is what we did in the symmetric case, the autocorrelation, you can see it's anti-bunching. And here, if we go in a non-symmetric position for the two detectors, I see the bunching. And if we plot this, we can see that we obtain anti-bunching and bunching in the different directions of the source, which is a little bit surprising because usually we think a source is uniquely determined by its photon statistics. Well, with these two atoms, you have bunched light emitted in one direction, as you can see here, bunched light emitted in that direction, and anti-bunched light emitted in that direction. So the same source emits different photon statistics in different directions. Okay, so this is maybe a good point. I have two slides for the classical light, but maybe it's not. No, that's fine. I mean, I will be very fast, just pointing out that instead of single photon sources, atoms, we can use also, of course, thermal sources, where the whole calculation in a quantum path picture becomes much more cumbersome, but you can follow it. You have to take into account that, as before, each source emits one photon, but it could be also that all m photons are emitted by the same sources, would be this expression, or one source emits m-1 photons and another one 1, and all the different combinations which you call partitions, which you have to take into account. But it turns out that all partitions, I'm very quick now, all partitions display this grating function. So you obtain the same behavior also for classical light. And so we did this kind of experiment. The visibility, though, is different for good reasons. The visibility is different. This is the experiment. I skip a little bit, show you maybe this result where we went up to the G8 function and where you cannot discriminate, in fact, the theory from the experiment because it's so much more easy to use classical light and with respect to quantum light, from single photon sources this is maybe, I skip it. This is where we are now. This is what I reported as a couple of years old sometimes, but this is where we are now. We are able to spin selectively excite the ground state of the calcium atoms because we use a two-photon excitation, which exploits this very narrow transition over here, so we can select the different Zeeman levels, whether spin down or spin up. So we can have spin selective excitation, which and obtain here also coherent emission, which allows us to determine whether we are in an antiferromagnetic or ferromagnetic configuration very quickly. And this is what we are looking next for quantum phase transitions and so on, but in the new setup. But I skip this. I just wrap up and would like to point out spontaneously emitting single photon emitters in entangled states emit super and superradiant light. I mean, this is known since '54. But superradiance understood as a consequence of single photon quantum passes constructively interfering in case of entangled decay states. We had this point of view of quantum passes interfering. And we learned that even completely uncorrelated single photon states, all in the excited state and a separable state, can be brought into an entangled state via conditional measurements, which turn out to be kind of HPT measurements. And so we can obtain superradiance also from completely uncorrelated, spontaneously emitting sources, either single photon sources or classical sources. And so I hope I can convince you that generalized HPT measurements just are a probe of superradiance and exploit the phenomenon of superradiance. And with this, I would like to thank the people of my group. This is a little bit surprising. Okay, I wanted to show many collaborators, but this is hidden by these pictures. From my group, especially Stefan Richter, Manuel Boye, and Siad Shehata contributed. This is the rest of the group. I wanted to show some collaborators, but this is somehow hidden by this. So I thank you for your attention.